Hello, am I audible? Hello.
Yes.
Yes.
Yes, ma'am.
Okay, and is my screen visible?
Yes.
Yes. Okay. So, good evening, everyone. I am Nidhi. I am a PhD student at ISER Mohali. I welcome you all to the problem. I welcome you all to the first problem solving session for NPTEL course Graph Theory. So, so the format of today's session will be first I'll briefly recall all the topics that were covered in the week one of the graph theory, and then on those we'll solve some questions on those topics. So uh, so uh, we'll begin in 2 minutes. I'm just waiting so that everyone can join, and we'll begin in 2 minutes. And in between, if you have any doubts, you can open out your mic and ask questions. Okay.
Madam, that PPT is not visible.
It's not visible.
It is visible.
Okay. Is it visible? My slide is visible, right?
Yes, madam.
Yes, ma'am.
Okay. Okay. Okay, so I'll start. So in week one, what was majorly discussed? Majorly, there was some basics of graph theory, and we studied Eulerian graphs and Hamiltonian graphs. So first, let's revise the basics of graph theory. So first of all, what is a graph? A graph is a pair of two sets which is comprises of v and which comprise of v, which is vertices, e, which is the edge set. So any graph is a pair of sets, set of vertices plus set of edges, and two vertices will be called adjacent if they have an edge between them. Now,
Madam, sorry, I am only looking you, ma'am. I am looking you, not the slides.
okay, wait. So is this problem is maybe so in your Google Meet maybe you haven't uh, you'll have to do some so maybe so is my screen visible to other people?
Yes,
Yes,
ma'am.
madam.
It's clearly visible for us.
Okay, so I think the one who for whom it is not visible, I think you have clicked on my picture. That's why it's coming. There must be some setting in which you have like you can view the screen. Please try. Are you able to see the screen now?
Yes, madam.
Okay. Okay. So the person who had problem is he able to see my screen? Okay. Okay, so start. So as I just defined what a graph was. Now there are some special type of graphs. So special types or some examples of graph. So first example is Kn, which is a complete graph, on n vertices. So by Kn we will mean a complete graph on n vertices, and by complete graph we means that all the vertices are adjacent to each other. Then other type of graph is Cn, which is cycle on n vertices. So basically we have n vertices and we are creating a cycle out of it. And another example of graph is trees. Trees is a simple graph in which there is no cycle. So if we have a graph which does not contain any cycle, then we call that graph as tree. So now I want so observe. Uh, if you have no question, can you please mute this? Yeah. Okay, so observe all these above graphs have no multiple edges and no self loop. So all such type of graphs are called simple graph, and in this course graph theory we will be mainly concerned with simple graphs, that is graphs without multiple edges or self loops. Now now the next concept is of a degree of vertex. So if we are given a vertex v, degree of vertex refers to the number of edges which are adjacent to that particular vertex. So you can see this 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 example of a triangle, it was a complete graph on 3 vertices, or K3. So what is the degree of each vertex in K3? Can anybody tell what? Yeah.
2.
2. Yeah.
Two.
So yes, so the degree of vertex is basically number of vertices which are adjacent to it. And the basic first result was that if you sum all the degree of the vertices, that sum will be equal to twice the number of edges. and 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 similarly, the other result was that for every graph, number of vertices with odd degrees will always be even. So now once we have done this, now there are some special kind of sequences in graphs. So first sequence is a walk is basically you are traversing edges in any manner, or it can be said as alternate sequence of vertices and edges. So walk means you are going from one vertex to other, and there are no restrictions. Now when you go to a trail, we have so trail is a walk in which no edges can be repeated. So as you can see, if as you can see in this following example, in this following example, this D AFDEBD BDF. So if we consider this is a walk. But if we repeat so if any walk in which no edges are repeated will be called a trail. And path has another restriction. In a path, it should be a walk in which no vertices are repeated. And a cycle is a closed walk in which no vertex other than the first and last is repeated. So now, and the other concept is of a connected graph. So what is a connected graph? So as the name suggests, if we'll call a graph connected if any two vertices can be connected by a walk. And components of graphs will be, so if we have a graph, so we look at the maximal connected subgraph of G, and those will be called the components of graph. And then lastly concept was a complement of a graph G. So if G is a graph, complement of graph G will be another graph which will have same vertices, but complement means that if E is any edge which is not present in G will be present in G bar. So G complement will comprise of all those edges which are not present in G. And then we had this result that if G is disconnected, then G bar is connected. So up till all these concepts, does anyone have any doubts in any of these definition? Oh,
So I have written a query in the chat box.
okay. Yeah, you can speak your query. Yeah. So what is, hello?
Yeah. So what's the difference in between the Eulerian path and the trail? And similarly, the difference in between the Hamiltonian path and the simple path, because the
Okay.
definition seems quite similar.
Okay. Yes. So Eulerian and Hamiltonian will come back later. We'll come back later. Yes, we'll discuss that. Among these topics till now, like, do you have any doubts?
No, it's clear. Yeah.
Okay.
Thanks.
Okay. Yes, we'll come back to it. Okay. So now first we'll look at some questions on these topics. Okay, so I have already written the question. I'll speak out the question. You can think about it, and if you have an answer, you can unmute yourself and speak out. So the first question. First questions are true and false. So first question is, every you have to tell is if it is true or false. So every disconnected graph as an isolated vertex. So isolated vertex means a vertex of degree 0. So is it true or false that every disconnected graph will have an isolated vertex?
False.
Ma'am,
False,
false.
false.
False. Okay, so can you give me so if it is false, can you give me an example why it is false? So,
Ma'am, two triangle, if we connect with one edge, and then if we cut that edge, then it will be two isolated triangle.
yes, good. So, uh, so right. So you are saying if we take G equal to this C D E F, this G is disconnected, but G does not have an isolated vertex. So your answer is correct. What about the second statement? Is it true or false that given a graph G or its complement G bar, at
False.
least one of them is connected?
It is true. It is true.
Okay,
Uh,
so somebody said false. So why is it false according to you? Yeah. So
It is true, ma'am. It is true.
so is everyone convinced that it is true?
yes.
Okay, so can somebody give me a reason why is it true?
Because both are mutually exclusive. So if we take the union of, say, union kind of the thing for the G and the complement of the G, this would result into a connected graph. So, I mean, wherever there is an edge in G, in what being those vertices, there won't be an edge in the complement of the G. So, one of them has to be connected definitely because their union would be connected.
So you are saying if union of two graphs is connected.
And if one is disconnected, then clearly the other one has to be connected. Otherwise, how would I get the union of both the graphs connected?
Okay. Yes. Okay. Yes. So basically, you are using the result that was proved in the lecture, that if G bar is if G is disconnected, then G bar is connected, right?
Yes.
Ma'am, can we take union of G and G bar?
Okay. So if you'll take union of G and G bar, it will give some another graph.
Yes, yes.
Yes. Yes.
So this analogy is not correct. We have to
Yes.
take G plus G bar.
Yes. uh, that might not, that is not correct, but his argument is still fine, that so basically we have this result that if G bar is disconnected, then G is connected, right? So so is everyone convinced that second statement is true? So
No,
basic
man. Please
Yes,
give some
yes,
justification.
yes. So uh, given a graph G or G, suppose this statement is, we'll prove it by contradictions. Suppose this statement is false, meant is false. Then if it is false, then what does that means? Basically, okay, yeah.
So both could be connected or disconnected simultaneously at the same time.
Yes. So given a graph G, at least one of them is connected. So I am saying that they. So if it is false, then that means we have some G and G bar such that both of them are disconnected. But is this possible? Can we have a graph G and G bar such that both of them are disconnected? Is that possible?
No.
No. Therefore, we have arrived at contradiction, and this statement is false. This statement is true. So is now everyone convinced that this statement is true?
Yes.
Any doubts in this statement?
Ma'am, this is because when we take the union, some edge will be missing, so we will not get the complete graph. And that is the reason, right?
Uh, that can be another reason, but this reason is also fine, right? That suppose both G and G bar are disconnected, But this cannot be possible, because if G bar is disconnected, then G has to be disconnected. G has to be connected. We have already proved it. That the what, right?
So the proof is coming from the third statement, second one.
Nine, the proof is coming from the result that we have proved in lecture, that if G bar is disconnected, then G is connected.
Okay, ma'am. Okay.
Yeah. Now, so now everyone is fine, right? With the second statement is true. Any doubts in second statement? Okay. So if not, now what about third statement? Third statement is saying that, okay, so I'll write, so we are using this result, in second statement we are using that if G bar is disconnected, then G is connected. Now, what about third statement? Is third statement true? Third statement says, third statement is like the converse of the result. So we are asking, if G is connected, can we say that if G is connected, then G bar will be disconnected? Is it true or false?
False. False.
Okay.
Uh,
Anybody think is it true? If it is true?
It is true, ma'am.
it is true because if we can traverse from a vertex to any other vertex in the graph G, and when we take its complement, then clearly that edge is going to be removed in the complement. So, yeah, so connectivity will get lost.
Okay. So can you please repeat your argument?
Yes, so if G is connected,
Hmm.
uh, it shows that we can make a move from a vertex to any other vertex in that graph.
Yes. Yes.
And now if I take the complement of the graph G,
Hmm.
then clearly that connectivity will get lost because whenever I find an edge in the graph G,
Hmm.
so I won't be having that edge in the complement of the graph.
Huh. But
So
so yes,
Madam, it is
but
false.
yes, yes, yes,
Madam, it is, madam,
yes, it is false. So I was just yes, you are right.
madam, I will
But
give you one example. If
huh,
you take C4,
yes,
ma'am,
okay.
C4, if you take, then
Anupam,
complement of
wait.
C,
Yes, Anupam, wait for a second. I'll listen to your example. I'm just telling why his argument is wrong. So basically, so in a connected graph, so connected graph says that there should be a path between any two vertices, and complement is basically if there is an edge between. So complement comprises of all those edges which are not present in G. So so it so you are saying that if there's a edge between v1 and v2, though that edge won't be there in G complement, but it is possible that there might be some other path in G complement. So if you are removing just one path between v1 and v2, that doesn't mean that you have removed all the paths. Hence your argument is not correct. Do you understand?
uh, yes, but there could be other path possible, right?
Yes.
But I do not understand that why the complement would still remain connected.
Okay, yes. So now Anupam has an example. So he'll tell us. Anupam, you were saying, you were telling an
ma'am,
example.
if
Yeah.
we take C4, ma'am,
Okay. Yes.
so C4 is connected, but if
Yes.
we take complement of C4, then it is also connected.
Yes. Good. So
So then
his
that means both are connected.
yes.
So
Yes.
that is why this is example which says that this
Hmm.
is false.
Yes. So Anupam has given this following example. So this is C4, right? What is the complement of C4? So basically, we have all these edges, and this edge is not present in G, so it will be there in G bar, and similarly this edge. So you see, C4 and C4 bar both are connected.
Ma'am, this complement is not connected, ma'am. How can
Why?
you say it is connected?
So why are you saying that it is not? Why you are saying it is? Oh, this complement is not connected. Yes, you are
Ma'am,
right.
take
Yes, yes,
ma'am
yes,
take P4. Ma'am, take P4, then
yes,
P4 is connected,
yes.
and the complement of P4 is also connected.
Okay. Wait. So yeah, yes. So Anupam, yes. Sorry, your example is wrong. Okay. So now, uh, So now there is another example. So this example won't work. Yes, you are right. So the other example is P4. So, or you can just take this. So, okay, sorry. So somebody gave an another example.
Ma'am, why can't we take a pentagon
Yes,
and its complement will be a star?
yes. This C5 will work. C5 will work. This is, and the complement will be star.
So here both are connected.
Both are connected. Yes. So now, and there can be many more examples. So we see that third statement is false. So is everyone fine with first question? Are there any doubts in the first question?
So, do we have meaning of connectivity for the directed graphs as well, or do we have a different interpretation of connectivity for the directed ones?
Oh, for directed graphs, uh, yes, for directed graphs, we can have two type of connectivity. One, we can view directed graph as a simple graph. Then our usual notion of connectivity will work. And other can be that there is a directed path. So depends. So both uh, but right now we are just concerned with simple graphs. So, but in directed graph there can be two notion of connectivity. Depends what you are working on.
Okay, okay.
Okay. So I'll go to my next question. If there is no doubt in this one. Okay. So now G is a so first of all, so when I'm saying graph, I'll always mean a simple graph. So now suppose G is, the question 2 says that suppose G is a graph with n vertices, and a part is that we have to show that there exist at least two vertices which have same degree. So any ideas how can we prove this? So G is a graph.
Yes, yes. So for the
Okay.
maximum degree of a vertex could be say n minus one in a graph,
Yes.
and if we so we can prove it by the contradiction. Say if we assume that all the vertices are having say different degrees,
Hmm.
so then can we construct a graph having say degrees ranging from
From
say starting from
zero.
one to say till n minus one?
Yes.
So yeah, this will
Yes.
definitely violate something.
Okay. Yes. Your idea is correct. So what he is saying is, we'll prove it by contradiction. Suppose all n vertices have distinct degree. This is degrees. So we have n vertices. So what are all possible degrees in a
One
simple
to
graph?
n minus one.
Are they all the possibility, or there can be anything else also?
0 to n minus 1.
Yes, correct. 0 to n minus 1. So how many numbers are there? So these are n numbers. So suppose all n vertices have distinct degree. So V1 will have, say V1 will have degree 0, V2 will have degree 1, V3 will have degree 2, and so on. So now tell me, is it possible to construct a graph which has following degree sequence? What do you think?
No, ma'am.
Everyone think, and okay. So there's an answer no. Does somebody have a different answer? Everyone think. So so the question is it possible to construct a graph with following degree sequence? That is, V1 should have degree 0, Now if V1 has degree 0, that means V1 is an isolated vertex. So now is it possible that if we have a degree 0 vertex, that means we have a vertex which is not adjacent to any of the other vertices. So now is the following degree sequence possible? What do you think?
No.
Okay, so we get another no.
So if I have the
Oh,
degree of a vertex
okay.
is n minus 1, then clearly there would be n minus 1 number of the outgoing edges from, or the incoming edges from n minus 1 number of the vertices. And now how many vertices are there? Say if we, so we'll have to exclude this 0 thing, and then from 1 to n minus 1 we are left with n minus 2 number of the vertices. So clearly, now in this case, without repetition, how is that possible that a vertex is having degree of n minus 1?
Okay. Yes, you're. So, so is it that? So, did you understand his argument? We'll repeat it obviously, but now did everyone understand why we cannot have following degree sequence? So basically, as we noted, now suppose all vertices have distinct degree. So now we have this vertex V1 which has degree 0, and we have vertex Vn which has degree n minus 1. So now is this possible? If
No.
degree of, yes, if degree of Vn is n minus 1, and since our graph we are already talking about simple graph, that and we have n vertices, that means Vn is adjacent to all other vertices, adjacent to V1 till Vn minus 1, and therefore degree of each vertex is greater than equal to 1, and we cannot have a vertex of degree 0. Therefore therefore we cannot have simple graph with above degree sequence. So did everyone understand? And therefore what we have assumed was false, and there should be at least two vertices which have same degree. So now is the A part clear to everybody?
And once we say that V1 is 0, that
Yes.
means it is an isolated node.
Isolated vertex. Yes.
It's isolated vertex or node. So then it is not a disconnect. It is already a disconnected graph.
Yes. Yes. That is fine. So we were asking that
So we should not take 0. We should start from 1.
no. So we are just so we are given that G is a graph. We haven't given that G is a connected graph. So we were just so we so our question was, given any graph G, no whether it is connected or disconnected doesn't matter. There should be at least two vertices which have same degree.
Okay. Okay.
Okay.
So with the same argument, if it is correct with a connected graph?
Yes. For connected graph, it will obviously follow, because in connected graph we don't have a option of 0, and
Yes.
and already we have n minus 1 value, so at least one value has to repeat. So for connected graph, it is already following from that. So this result is true no matter whether the graph is connected or disconnected. We didn't put any condition on our graph except that it is a simple graph. So is the first part clear to everyone?
Yes.
Okay. So now the p part says that, so b part says that if G has n plus 1 edges, then we have to show that there exists a vertex of degree at least 3. So so B is, order of vertices is n, order of edges is n, number of edges is n plus 1. Then we have to show there exists one vertex of degree at least 3. Okay. So first of all, you can now first of all, what now we are given that number of edges is n plus 1. Number of edges are n plus 1. So what can we say about sum of all degrees? Can we say anything about this? If we are given that number of edges are n plus 1, what can we say about sum of all degrees of the vertex?
So
2n plus 2.
yeah, this
Yes,
says that
this is
yeah,
2n plus 2. So
yeah.
now, sorry, 2n plus 2. So by handshaking lemma, we know it is twice the number of edges, which is 2n plus 2. So now we have n vertices. Now we have n vertices whose sum of degree is 2n plus 2. And we have to show that there should be at least one vertex whose degree is greater than equal to 3. That to show there exists V such that dV is greater than equal to 3. So suppose we want to prove it by contradiction. So can you so the suppose suppose all vertices, suppose we don't have we'll prove it by contradiction. Assume on the contrary that all vertices have degree strictly less than 3 or less than equal to 2. Now can you see the contradiction?
Yes, yes. Because now, if we consider the degree of every vertex is less than or equals to 2, then at the most we can have the sum in the left hand side as 2n, right? And which is clearly smaller than the 2 of n plus 1. So definitely, one vertex is having the degree higher than 2.
So did everyone understand his argument? So what is he saying? That now we are assuming that all vertices have degree less than equal to 2. Therefore we have dv is less than equal to 2 for all v in vertices of G. So now sum of all the vertices. So we have n vertices, and we are given that each vertex has degree less than equal to 2. So we get that sum of all vertices is less than equal to 2n. But but since this graph has n plus 1 n plus 1 edges, sum of degree was given to be 2n plus 2, which is strictly less than 2n plus 2. So we have arrived at a contradiction. Hence, there exists a V such that degree of vertex is greater than equal to 3. So now, did everyone understand? Did everyone understand the second part of this? Or any
Ma'am,
doubts?
if we take n is equal to 1 vertex, so right hand side is equal to 4.
Wait,
If we take n is equal to 1,
yes.
so then right hand side is 2 plus 2 is 4.
So, okay, right.
No,
So
no, but it is
how
given
to
that
how to
G
realize
has
that?
n
But
plus 1
if we,
edges.
but it yeah. So if you have
So,
one vertex, you cannot have two edges, right? So you are
yes.
given that G has n vertices and n plus 1 edges. So n equal to 1 case doesn't cannot happen here. Is your doubt?
Why we can take a star with one node and two edges?
Sorry, star with one node and two edges, as in.
So if we take one node inside and two edges going outside.
But no. So what is the number of what is the number of vertices there in your example? So if you are taking star and two edges going out, then that means that graph has three vertices and two edges. So it is not satisfying the hypothesis of the of the B part. B part is just saying that if G has a graph with n vertices and n plus 1 edges, then there should be a vertex of degree at least 3. So is it clear? Is the B part clear to everyone?
Yes, ma'am.
Ma'am, you just draw one node and two branches going out as a tree. Then this is not happening.
Yeah. So you are saying this, right?
Yes, yes.
So now see, this graph has three vertices.
No. You put one center as a vertices. One center and two edges going outside.
Ma'am,
Center.
the
But
edge won't be.
this is not possible, right? If you have an edge, that edge should by edge we mean that edge should connect two end points of the edge should be vertices. In a graph, end point, what is an edge? Edge is basically a line which is joining two vertices. So this is not a graph. So this thing is not a graph if these two are not vertices.
In that case, ma'am, any tree is not a graph then? Tree with one node and two leaves are not a graph then?
So
Then it contains three,
this
at
is a
least three.
tree. This is a tree, but these two are also vertices. Your leaf is also a vertex.
Okay.
Yeah. Is your question clear now? So
Yes.
in a graph G, all the endpoints of in any graph, endpoints of edges should be vertices. This is the definition of graph. Okay. So now I move on to the okay. Okay, so now there is this question. So whenever we have some statement like this, we want to know if the number that is appearing is best possible. So we are saying that if G has n vertices and n plus 1 edges, there will always exist a vertex of degree 3. So is this 3 number, there will be a vertex of degree at least 3. So is this 3 number best possible? So, so I am saying that if number of vertices is n and number of edges is n plus 1, can we always uh, guarantee that there exists a vertex, of degree at least 4? So in previously we showed that in this case we can always guarantee that there will be at least one vertex which has degree greater than equal to 3. So the question is, can we improve this result? Can we say that there exists a vertex of degree at least 4? Yes or no?
Yes, 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 ma'am.
Why? Why? Then you'll have to give an argument also.
So, ma'am, this that result you said 2n plus 2. So now if we take n is equal to 1, so right hand side it is degree is coming as a 4.
Hmm.
So can we prove this by induction?
Okay. So I'm saying, okay. So I'm saying this is false. That we can, uh, this result is best possible. That is, it is not necessary that if you have n vertices and n plus 1 edges, there exists a vertex of degree at least 4. That is, you can find a graph with n vertices and n plus 1 edges which has no vertex of degree less than equal to 3. So now can you find such graph?
So, for the validity of the question, the number of vertices should be at least three.
Yes.
Then only we can have the number of edges is equal to one plus the number of the vertices.
Yes, that is true. Yeah.
So if we use a similar argument here and assume that every vertex is having degree at least three,
3.
so
Yes.
then we'll come up with this with an inequality wherein
Hmm. Hello.
of the least degree of vertex.
Hello.
Screen is not visible.
Yes. Sorry, I got disconnected for a bit. Is it visible now?
Yes.
Yes. Sorry, I got disconnected. So I didn't hear the last argument. So somebody was given. I think somebody was giving an argument why it is not true. Right?
So yeah, so the num so the least number of the vertices here should be equals to three. Number one,
Yes.
and
Yes.
second, if we assume that the degree of every vertex is three, so
Hmm.
then this inequality will become that the value of n should be less than two.
Hmm.
Right. So that leaves only one possibility wherein we have a single node. However, with a single node, clearly we cannot have say two edges. So
Hmm.
therefore, this is false. This is the upper bound of the least degree of a vertex. I mean, with the given
Yes.
parameters.
Yes. So we are just saying that there exists a vertex of degree. So what you are saying is it kinds of gives us an idea that we can. So if it was true, we cannot prove it using the same argument because of that what the argument. But now if we have to say that some statement is false, we have to give a particular example in which this is happening. That is, we have to give a graph with n vertices, n plus 1 edges, and which has no vertex or degree 4, degree at least 4. So can somebody give me an example? Say any, so can, yeah.
Add one diagonal edge basically, then we have basically none of them vertex has degree 4.
Yes, so are you saying this example, if we take n equal to 4 and we take 5 edges,
Yes,
5
ma'am.
edges, then we see that there is no vertex of degree at least 4. So this so this shows that 3 is the best possible answer for this situation. That if we have a graph has n vertices and n plus 1 edges, at most we can guarantee that there will be a vertex of degree at least 3. And for degree 4 it is false. And which is the example is given by one of you is this. So this has 4 vertices, 5 edges, but no vertex of degree at least 4. All the vertices have degree less than equal to 3. So now is this question clear to everyone?
Yes.
Yes. Okay. Now, next question says that there are 15 telephones in an area. Is it possible to connect them in a manner such that any telephone is connected with 5 other telephones? So now tell me if this is true. So first of all, we have to convert this problem into a graph theory problem. So first we'll convert this problem into a graph theory problem, and then we'll see if it is possible or not. So if we want to convert it into a graph theory problem, so what is the candidate for vertices?
Telephones.
Telephones. Yes. So we can let telephones be the vertices. So we have 15 vertices, T1, T2, T15. And what are the edges? So what are the edges?
So connectivity among the telephones
Yes.
will
So we
form.
say TI, TJ is an edge if TI and TJ are connected. So now the question is, can we have a graph with 15 vertices such that each vertex is adjacent to 5 other vertices? So what do you think? Is
No,
it
ma'am.
possible?
It is not possible.
Why?
Ma'am, basically, if we take degree of each vertex, in this case, so that will be 5. So
Yes.
then by using hand-shaking lemma, sum of degrees of vertices, that should be even. So basically, in this case, it will be 5 times 15. That is not a even, ma'am.
Yes, very good. So what is he saying is, basically this says that suppose it was possible, then this will say that degree of each vertex is 5. And if we sum all the vertices, then it is coming out to be 15 into 5, which is odd. And this cannot be possible by
And
handshaking lemma.
moreover, we can never we can always have the even number of the vertices having the odd degrees. So now here we have a 15 number of the vertices having the odd degree 5. So that is also not possible.
Yes.
Another argument. Yeah.
Yes. So the equivalent statement of handshaking lever is that in a simple in that or in a graph, the odd vertex should be even. Basically, the vertices with number of vertices with odd degree should be even. And in this case, we see we have odd number of odd vertices. Therefore, this is not possible. Good. So that is also a nice argument. So now what about B part? So now, so is everyone clear with the first part? Okay. So now B part says that can we have a simple graph with following degree sequence? So everyone please look at this degree sequence. These are 8 vertices. Now, now think if we can have a graph with following degree sequence or not. So so firstly, if you have an answer, just say yes or no. Then we'll see.
No,
Okay, so there is one candidate, there's one person who thinks no. What about others?
No,
Okay,
ma'am.
no. Yes, so there are a lot of no's.
No, no.
Okay, so S and Trisha has raised her hand. Yeah.
Yes, ma'am. It is possible, ma'am.
Okay. So somebody says it's possible. So S and Trisha has raised her hand. Do you want to say something? Okay. So, okay. So somebody said, is it possible? Yes, Anupam said it's possible. So Anupam, why it is possible?
Ma'am, the odd degree, if we say 7, 7, 7, and 3,
Hmm.
they are even.
Hmm.
So then, as we said, that odd degrees must be even. So there, the graph is possible.
No, no, no. So,
That is not a
not
sufficient
this
condition.
is
That is
the
only necessary condition.
yes, this is what you are saying is the converse. So we have said that if G is a graph, then the number of odd vertices should be even. But the other way around is not true. That if the number of odd vertices are basically, if in a degree sequence odd vertices are even, then we should always have a graph. So the converse need not be true. Okay. Right, we have only handshaking lemma just says that if G is a graph, the number of odd vertices should be even. It doesn't say the other way around. Is it fine? Is it fine that why can't we conclude using handshaking lemma?
Yes.
Yes. Okay. So now, so somebody said no. So who wants to answer, like, why is it not possible?
Ma'am, every vertex should have degree at least 3, but there exists a vertex with degree 2. That is why it is not possible.
Okay. So, so he's saying that every vertex should have degree at least 3, but we have a vertex of degree 2, therefore not possible. So he is right. So now somebody else tell me so why is he saying that every vertex should have degree at least 3? If somebody, if otherwise we'll ask him only. So why is, so from this degree sequence, why can we conclude that every vertex should have degree at least 3?
Because there are three edge vertices with edge with 7 degree 7, which is n-1.
Yes.
So there should every vertex should have degree at least degree of 3.
Yes, very good. So we can see that this G, this sequence has 8 vertices, total 8 vertices, and 3 vertices with the degree 7. So that means each vertex should be adjacent to at least 3 vertices. But we have this one which is has just degree 2. So this is not possible. Therefore, we cannot have a simple graph with following degree sequence. So is question 3 also clear to everyone?
So, do we have a proof of this conclusion that if we have k number of the vertices having n minus 1 degrees, then definitely the least degree of a vertex should be equals to k?
So this is the proof only, right? So so we have three vertices with degree 7. Suppose those vertices are v1, v2, v3, right? So if you pick any other, so if you pick any, okay, so we have v1, v2, v3. So we have these vertices v4 till vn, and suppose these three vertices have degree 7. So now if you pick any vertex, it is connected, it is adjacent to v1 also, v2 also, v3 also. Therefore degree of vertex, so degree of vertex other than v1, v2, v3 should be at least, so should so no sorry yes, so if we pick, so for v1, v2, v3, degree is already greater than equal to 3. Now if you pick any other vertex other than v1, v2, v3, since these vertices have degree 7, they are also adjacent to v1, they are also adjacent to v2, they are also adjacent to v3. So degree, their degree should be at least 3, right?
Yes, yes. I mean, according to the common sense, it's okay. But then, how can we write proof of it? What
Okay,
could be the outline of the proof of this?
okay. So this is okay. This is a proof only. So suppose, yeah. So I'm just saying, let v1 dv1 dv2 equal to dv3 equal to 7, which is already greater than equal to 3. Let v4 belongs to let v4 belongs to vertex such that v4 is not equal to v1, v2 or v3. Now degree of each vertex is 7. Therefore we have that v4 v1, v4 v2 and v4 v3 should be an edge, should be an edge in G. Now what is the meaning of degree, or what is the meaning of degree of vertex? It is the number of vertices which are adjacent to v4. So we have already v4 v1 is an edge, v4 v2 is an edge, v4 v3 is an edge. So we get that degree of v4 should be greater than equal to 3. So this is a proof only, right?
Yes, yes, I understood. The only thing probably remaining here is that we could have written that we arrange the vertices in the decreasing order of their degrees and say V4 is the one which is having the least degree, and then we can continue with this argument. Yeah,
Yes, yes. Yeah. Yeah.
fine.
Okay. Okay. So now is this question clear to everyone?
Yes.
Yes. Okay. Okay. So now we'll talk about Eulerian graphs. So I'll just recall first of all what is an Eulerian trail. So now now next two questions will be on Eulerian graphs. So first, so what is an Eulerian trail? So if we are given a graph G, a trail will be called an Eulerian trail. First of all, it should be closed, and secondly, it should contain all edges of a graph. So now there was a question how Eulerian trail is different from an ordinary trail. So ordinary trail just says that it should so so Eulerian trail has this additional condition that that trail should contain all the edges. But normal trail is just a walk in which no edge is repeated. So if we look at this G, if we look at this G, this is a very simple graph, but A B C D E. So we see that A E D C B A is an Eulerian trail, and AED is a trail, but so the difference between Eulerian trail and an ordinary trail is just that ordinary trail need not consist of all the edges, but for oil and also it should by Eulerian trail we don't ordinary trail, the first vertex and last vertex this condition is also not required, that first vertex or last vertex is should be same. So but also Eulerian trail has two more conditions. First of all, that first vertex and last vertex should be same, which is what is closed means, and secondly it should contain all edges of a graph. So somebody in the beginning asked what is the difference between Eulerian trail and ordinary trail. So is it now clear to him what is the difference?
Yes, yes, yeah.
Yeah.
Thanks.
Okay. Yeah. So now this is
So
an
Eulerian tail is, ma'am, closed. Closed.
closed. By closed we
So
means that the first vertex and the last vertex should be same.
then it is a circuit, na? So same, it is circuit. Eulerian circuit.
uh I think in circuit so it depends on the terminology, but in circuit you might have that condition also, that no vertex is repeated, but in Eulerian trail we don't demand any such thing.
So actually, can I say something?
Yes, yes, sure.
Yeah. So we in ordinary trail we have this all edges should be distinct. All edges should be distinct, but we
Yes.
don't need to have distinct edges in Eulerian trail.
No, no. on, or we should have distinct edges in Eulerian trail, because Eulerian trail is a trail itself.
So for having an Eulerian trail, we must have a trail. Then, and if we include all the edges of the graph and make it closed, then it becomes Eulerian trail.
Yes, yes.
Okay. Okay.
So I think that this Eulerian trail corresponds to the Eulerian circuitry. And because in the case of the Eulerian path, we would be covering all the edges. However, the initial and the end vertex would be different.
Okay. Yes, so there might be different terminologies for the same thing, but here I am considering Eulerian trail as the as a Eulerian trail should first of all should be a trail. Secondly, it should be a closed trail. That means the first vertex and last vertex should be same. And thirdly, it should consist of all the edges of the graph.
Yes. So
So
then it is Eulerian circuit.
okay, so to avoid confusion, let's not bring on other terminology. For now, stick into Eulerian trail only.
Yeah, sure, sure.
and and so if a graph will have a Eulerian trail, then that graph will be called a Eulerian graph. And in the lectures, sir has already proved that a connected graph uh, is oil he has proved it for more general multigraph also. A connected graph or multigraph is Eulerian if and only if every vertex has even degree. That means every vertex should be adjacent to even number of vertices. So now, is the definition of Eulerian trail and Eulerian graph clear to everybody? Okay, so
Ma'am,
now
please repeat the condition. Please repeat the condition
for condition for
for that graph which is Eulerian.
so if we have a graph G which has an Eulerian trail, then that graph will be called an Eulerian graph.
And what is the condition for n nodes?
As in n nodes, as in
You said no, sir has given
yes.
some.
So yeah, I have written the result. So a graph will be called Eulerian if and only if every vertex has even degree. So basically if you want to see if the graph will have Eulerian trail or not, you just need to look at the degree of each vertex. If degree of each vertex is even, then from that result we can directly conclude that that graph is Eulerian. So that is the condition. Is it clear? Is this what you were asking?
Yes, ma'am.
Okay. So now if the definition of Eulerian trail is clear, we can move on to the questions.
Yeah, sure.
Yeah. Okay. Okay. So, uh, okay. So we'll return back to question 4. First, we'll do question 5. So, everyone know what question 5 says. Is Kn Eulerian? Kn is complete graph,
With k vertices.
complete
K
graph
regular
on
graph.
n vertices. So, what do you think? Is it Eulerian? Complete graph on n vertices. So okay, so for we are basically for what values of n is Kn Eulerian. So let's draw something. So suppose first of all we talk about K3. Is K3 Eulerian?
Yes.
Yes, ma'am.
Yes, ma'am.
Yes,
Yes.
ma'am.
Yes,
Yes,
because
ma'am.
we can consider the Eulerian trail V1, V2, V3 itself. What about K4? Is K4 Eulerian? No.
No, ma'am.
No, ma'am.
Why?
Because of our degree.
Degree is not even.
Yes, because degree of each vertex is 3, which is odd. Therefore, from that result, we can say that K4 is not Eulerian. So now can you generalize?
Kn is Eulerian if and only if n is odd.
Okay, so somebody said we can say that Kn is Eulerian if and only if n is odd. So does everyone agree with him? Okay. So first of all, tell me, Kn is a complete graph on n vertices. So what is the degree of each vertex in Kn?
N minus 1.
Right? Degree of each vertex is n minus 1. So is everyone clear why? So complete graph says that, what is the definition of complete graph? Complete graph says that any vertex is adjacent to every other vertex. So if we have n vertices, and we have vertex v, if we have any n vertices, it will be attached to all other vertices. So what will be the degree of each vertex? N minus 1. And our result says that G is Eulerian if and only if all vertices have even degree. uh, all vertices have even degree. So when is n minus 1 even?
When n is odd.
When n is odd. Therefore, the claim is right that Kn is Eulerian if and only if n is odd. And we can also say that n is greater than equal to 3, because if we have one vertex, we have no edges. So is this fine that if Kn is Eulerian, n is odd? Because if n is even, then all the vertices are odd. So the question 5, which says for what values of n is Kn Eulerian? So the answer is for n odd. So is everyone convinced? Is everyone convinced with it, or any doubts in this?
Yes.
Okay. Now second part of this question is KMN. So is everyone aware of this notation? What is this notation?
Yes.
Okay. So what is this notation?
Bipartite graph with m and n nodes.
Yes. So okay, I'll define this. So what do we mean by KMN? KMN is complete bipartite graph complete bipartite graph uh, on two partitions V1 union V2, where order of V1 is m and order of V2 is n. So what do we mean by this? First of all, what is a bipartite graph? First of all, what is a bipartite graph? Bipartite graph is any graph G which can be partitioned into graph whose vertices can be partitioned into two sets V1 and V2, such that there are no edges in V1 and no edges in V2. So basically what we are saying that our graph has can be whose its vertex set can be partitioned into two two cells such that we have some vertices there and some vertices here, and there should be no edges between the vertices of V1. All the edges should be going like this. That is, if E is an edge in G, one endpoint is in V1 and one endpoint is in V2. V1 and one endpoint in V2. So this is a bipartite graph. So is everyone aware of bipartite graph, and is everyone understand what is a bipartite graph?
Yes.
Any doubts on the definition of bipartite graph? Okay. If no, now we'll see what is KMN. So first we'll do it with some examples. So suppose what is K23. So first number is saying that in V1 we have two vertices, and the second number is giving the order of third set, and complete bipartite graph means that every edge of this every edge of every okay sorry so this is my big V1 and this is V2. Complete bipartite graph means that every vertex of V1 is connected to every other vertex of V2. So basically V1 will be connected to W1, W2, W3, and V2 will also be connected with W1, W2, W3. So this is complete bipartite graph. K on one this is K23. So now if you want to write KMN, that means that first set will have M vertices, second set will have N vertices, and we'll have all the edges. Basically, uh, each VI will be connected to all other WI. So, and it is called complete because this, like basically, if you have M vertices, N vertices, this is the largest possible edges of a bipartite graph. So now, is everyone clear with the definition of complete bipartite graph also? Any doubts? Any doubts? Okay. So now if there are no doubts, so now tell me, oh, yes, is K23 Eulerian? Is K23 Eulerian? So
No.
what? Okay. So there is
No,
a
no.
why?
Because degree of V1 and V2 is 3, 3, ma'am.
Yes. Good. So we have that K23 is not Eulerian. So now if we have KMN, what is the degree of VI? In KMN, what is the degree of VI?
And
N.
Yes, because each vertex is connected to all other vertex here. So degree of each VI is N. And what is the degree of each WI?
It
M.
is N.
It, yes. So it is M. So now when will be KMN Eulerian? So what
if
values of M and N will be KMN Eulerian?
Both are
if
even, ma'am.
both
Sorry.
And
Both are the same.
and both even.
Yes. Both, if both M N are even, then KMN is Eulerian. Good. So, for fifth question, the answer is, for what values of Mn is Kn Eulerian? For Kn, N should be odd, and for KMN, M and N should be even. So, is question 5 clear to everyone?
Yes.
Okay. Any doubt
Madam,
in?
what is the advantage of this finding this Eulerian? Please can give you some examples also, application.
Hmm. Okay. Uh, so I don't have any application right now. I don't know I have any. So Eulerian are special kind of graphs. Basically it is basically if you have a if you are modeling something in form of a graph, and if you want to check that there is a if you want to check that there is a path which is covering all the edges, if you want to see if you then then this gives you an answer.
Like that famous bridge which is
Yeah.
there, it is not an Eulerian. So
Yes,
there is
yes,
no path. So that
yes,
is the example.
yes,
So
that is
now,
an
is there
example. Yeah.
any example which is beyond that? So that example we know, but any other example?
Okay. So right now I don't know any example, like any famous example, like the the Königsberg problem. So major, so application will be this only. So Königsberg bridge problem is basically you have all these bridges and cities, and the question is, if you want, can you go over all bridges exactly once? Like there are some cities and there are some bridges. So and the
So for that, this is example that there is no Eulerian path. So
huh,
that
yes,
is the example.
yes.
So
So
so my
similar,
point is, ma'am,
yes, similar.
any other such examples, if you can, from next onward, so we can relate the subject more.
Okay, yes, I look at, like, if like look for some application of Eulerian graph. So right
Yes,
now
ma'am.
what I can think of is just that basically it can be like, basically if you have a similar problem that you have some vertices and you have some connection, and if you want to see if you can traverse everything, then this gives you a nice answer that you draw a graph, and if all the vertices have even degree, then you can do that. Okay.
Thank you, ma'am.
uh okay, so now we have question 4. This, I'll write it in a different page. Question 4 is that G is a connected graph on n vertices, and we need to show that G has at least n minus 1 edges. So we'll prove this by induction. So so the question is basically we so if G is a simple connected graph on n vertices, we have to show that that graph should have at least n minus 1 edges. Okay. So we'll prove it by induction. For n equal to 1, is this statement true? So we are basically just saying that number of edges should be greater than equal to 0. And if we have one vertex, the number of edges is 0. So for n equal to 1, it is trivially true. Now we assume the result. So we are doing it by induction. So we assume the result for k vertices when k is less than n. And now we'll show for k equal to n. So did everyone understand the question? So first of all, if there's a doubt, what is given to us and what we have to prove. Any doubts in that? Okay. And this n equal to 1 case is also trivially true, we have seen. And now we are using basically strong principle of induction, which is we are assuming the result for all values strictly less than n. And now we'll show for k equal to n. Now suppose G is a connected graph on n vertices with the least number of edges. So basically, so we are looking at all the connected graphs on n vertices, and we are picking that graph which has least number of edges. And if we can show the result for this, then we have shown it for all the graph on n vertices, right? To show number of edges in G is greater than equal to n minus 1. Now, if G is a connected graph on n vertices with least number of edges, what does that mean? What is the advantage of picking such a graph? So we have picked a connected graph on n vertices with least number of edges. What happens if we remove one edge? Will that graph remain connected or not?
Will become disconnected.
Sorry? Yeah?
So if we remove one more edge, then since this is the lower bound, so if you
Yes.
remove one more edge, so then the graph will become disconnected.
Yes. So let E belongs to G, and since we have picked the graph with connected graph with least number of edges, then we have that G minus E is disconnected. Or G minus E has two connected components. Also, so this, so we have that G minus E is disconnected. So now my second other statement is saying that G minus E will have two connected components. So do you think is it true that if we have a connected graph and if we are removing one edge, and if it is becoming disconnected, then it will have only two components? As in, if we are removing one edge from a connected component, if we are removing one edge from a connected graph, we cannot, the new graph will have less than equal to two component. Do you think why is it true?
There would be a bridge kind of a thing or what?
Yes. Yeah. So you are right. So why this is true? So this is true because suppose we have suppose we have more than more than two components. So you suppose we have more than two components. Suppose we have three components. So one edge, so if a graph has three components, one edge, adding one edge won't make that graph connected, right? If we are adding one edge, we can only uh, uh, we, uh, uh, if we are adding one edge to this graph, can this graph become connected? Suppose we have a graph G which has three components and we add one edge to that graph. Will that graph can that graph become connected?
No,
No.
we have to add at least two
We have
edges.
to at least add at least two edges. So hence this is true, that if G is connected and G minus E is disconnected, then G minus E will have exactly two connected components. So is everyone convinced with this line? Any doubts up till now? Okay. So now we have that G minus E has two connected components. Suppose they are C1 and C2. These are the two components. So we have some vertices here, V2, which are connected, and we have some vertices here. Suppose C1 has M vertices and C2 has R vertices. So this M is strictly less than N and this R is also strictly less than N. So this is G minus E. This graph is G minus E. It has two connected components, say C1 and C2. Now can we use induction? Can we use induction on C1 and C2? C1 is a connected graph of M vertices. So what can we say about the edges of C1?
So if we have m number of m number of the vertices, so then there would be m minus 1 here, and then for the second component r minus 1.
Yes. So basically using induction hypothesis.
But here we are using complete induction.
Yes, yes.
Yeah.
Strong principle. Using induction hypothesis, we have number of edges in C1 is greater than equal to M minus 1. And similarly, number of edges in C2 is greater than equal to R minus 1. So now what can we say about the number of edges in G? So and there is this E is here. So we started with a connected graph. We started with a connected graph with a minimum number of edges, and we removed one edge from here. Then we get this following graph. G minus E, which has two components, C1 and C2. First component has M vertices, other component has R vertices. So now and from induction hypothesis we get that edges in C1 will be greater than equal to M minus 1 and edges in C2 will be greater than equal to R minus 1. So what can we say about the edges in G?
N minus 2. M plus r minus 2 and m plus r is equal to n.
So number of edges will be our total. What first of all, yeah. So number of edges in G is same as number of edges in C1 plus number of edges in C2 plus 1, because there's this edge E also, right?
Yes.
So this will be greater than equal to M minus 1 plus R minus 1 plus 1, which is equal to M plus R minus 1. And what can we say about n plus r?
Equal to n.
N. Yes. So, so we get that number of edges in G is greater than equal to n minus 1. And this is what we this is what we wanted to prove. So is everyone clear with this question? That is, a connected graph on n vertices should have at least n minus 1 edges.
With two step with n is equal to 1 and n equal to 2 and n equal to 3, we can prove this result. So why we are going for generalization
As in,
as a general case? And we can prove this by taking 1 n is equal to 1 n equal to 2 n equal to 3.
as in you are saying we can prove it using normal induction. We don't need to use strong principle, you are saying.
Yes, yes.
So what is your argument? How can we do that?
Say suppose we have to assume that n is equal to k is with one node, and then again we can say n plus 1 with another node. So it is coming, it is same in the same similar line, we can say like this.
No. So I'll tell you what will be the issue. So for n equal to 1, this is already true. Now assume result for n minus 1 vertices. And we want to show it for n vertices, right? So suppose I started with a G is a graph with n vertices. G is a connected graph with n vertices. G is a connected graph with n vertices and least number of edges. So now how will you prove this? Yes.
C1 component with n minus 1 nodes and another node outside. So and then we have to connect with one edge.
So now why will C1 be connected? But why C1 will be connected? That is the issue, right?
So ma'am, we are coming from 1 n is equal to 1 n equal to 2 n equal to 3 like that, na? We have to assume that it is connected. We have to assume in the induction, we have to assume that.
Yes, no. So in induction, we assume that G is a graph with n vertices. G is a graph with n vertices and G is connected. Okay. But why? What I am saying is why if we remove one, like why can we have this case that if you take one vertex outside, that the remaining graph will be connected. This can be a scenario, right? See, this is a connected graph. This is a connected graph. But if I'm considering this vertex, if I'm at here, so here this will be just this C1 will be this. So now this C1 is not connected, right? So hence you can't use the usual induction. So you cannot guarantee that if you take one node outside and you look at the remaining graph without that node, that graph is connected. Do you understand the problem?
Yes, yes.
Okay. So is everyone clear with this question 4? Any doubts in question 4?
Why do you add 1, ma'am? E of
Sorry.
C1 plus E of C2 plus 1.
Sorry, your voice broke down. I couldn't hear. Yeah. So
No, ma'am, why do you add that 1, ma'am?
yes,
E of
yes,
G equal to
yes,
1.
yes. So see, so basically G minus. So our graph. So we started with a graph with n vertices, but E was also an edge of G, right? E is an edge of G which is not present in either C1 or C2. So if we want to look at all the edges of G, it will be the all the edges which are in C1, all the edges which are in C2 plus 1. Plus 1, this correspond to the edge E. Is it clear? Hello? Yes, ma'am. Okay. Now, any other doubts in this question?
So this is the lower bound, and what could be the upper bound? Except that the since the graph is connected, so there would be NC2 number of the edges.
Yes, sir. Yeah. So if it is a simple graph, you can NC2 is the upper bound, right? Complete graph basically. Complete graph on n vertices is connected, and that is the largest possible number of edges,
Okay.
right?
Okay, because in the yesterday's solving session, we saw one question in which
Hmm.
a proof was given that we can relax this constraint by an amount of n minus 1 C2, and still the graph would remain connected. Yeah. So probably that was a proof given to us, I think, if I correctly remember. That even though NC2 uh, is an upper bound clearly, but then this can be relaxed by some amount, and still the graph.
No,
Uh,
no. I think what you are saying is this. I think the you are talking about degree of vertex. If I am not wrong, I think I don't. Is this was the question? If degree of each vertex is n minus one, choose two, then the graph is connected. Something like
num-
this, or
number of edges, because
acha
if
number of edges. Okay.
yes, because if the graph is connected, then clearly there would be NC2 number of the edges.
Yes.
So
Yes.
can
Yes.
you
Yes. Yes.
Ma'am, for degree case, it should be the minimum degree is greater than equal to n minus 1 by 2. Then the graph will
Yes.
be
Yes. Yes.
connected.
Yes.
That is for the degree.
Okay. Yeah. Okay. Yeah. Obviously. Yes. And so okay.
And
So
one related question: would you be sharing this OneNote file with us?
yes. 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 The
Yeah.
PDF.
Yeah.
PDF.
Thanks.
Okay. So is this question any doubts in this question?
Ma'am, why not that normal induction? That is not clear. Why it is not working?
So see, I'm saying the normal induction is not working in this scenario because so if we want to use the normal induction, so we'll say that if we remove, so we have to guarantee that if we remove one vertex, then there is a graph. If we remove one vertex, then the graph on n minus 1 vertices should be connected. But like in this case, if we remove this vertex, this C1 won't be connected, right? So we can't apply induction argument here.
Which one, ma'am?
So I'm saying that so if in this example, see this one, I'm saying if we look at this, if we have to apply induction, so suppose I have assumed the result for n equal to 3 and I want to show for n equal to 4. If this was my graph, and if I have to apply induction, I should be able to guarantee that there is a connected subgraph of n minus 1 vertices, right?
Okay.
But that is not clear why it should always be there. If we that if we can prove that first, then
With induction hypothesis, we can assume that that C1 is connected with the minimum number of edges, say n minus 1.
no, induction hypothesis is just so induction hypothesis is saying that result is true for n minus 1 vertices. That is, if G is a graph with n minus 1 vertices, G is a connected graph with n minus 1 vertices, then G will have at least n minus 2 edges. So induction
Okay.
hypothesis require the graph to be connected. But if so, normal induction hence here is not working.
Okay, understood, ma'am.
Okay. Okay. Okay, so now we'll move on to the last topic, which is the Hamiltonian cycle. So what is an Hamiltonian cycle? Hamiltonian cycle is a cycle in a graph G which contain all the vertices of G. Okay.
Ma'am, I have a question.
Yes, sure.
In a Hamiltonian cycle, does the path have to cover all the edges? Like the path, there will be a path for a Hamiltonian cycle. So will it cover all the edges like it covers in an Eulerian graph?
No, no, no. So Hamiltonian cycle just require
And
that.
also,
Yeah.
also will the starting and end vertices of the Hamiltonian cycle be same?
Yes, see, yes. So Hamiltonian cycle is a cycle. So by cycle, what do we mean? Cycle is a closed path. That is, that is, cycle is a closed path. That is only we have a path on which only first and the last vertex is repeated. We are allowed to repeat basically. In between, there should be no repetition of the vertices. So cycle is a closed path. So Hamiltonian cycle is a closed path which contain all the vertices of graph G. And as you asked, it need not contain all the edges, but it should contain all the vertices.
And in an Eulerian graph, it should contain all the edges. The starting and end vertices should be same, and no vertices should be repeated.
No, no. In an Eulerian trail, we are allowed to repeat the vertices, but we are not allowed to repeat the edges.
Okay, ma'am. Thank you.
Yes. Okay. And so somebody asked in the beginning, what is the difference between an ordinary cycle and a Hamiltonian cycle? So can anybody tell me what is the difference between Hamiltonian cycle and an ordinary cycle in a graph?
That Hamiltonian cycle must contains all the vertices of the graphs, and the cycle basically need not to contain all the vertices.
Yes, very good. So that is the difference between Hamiltonian cycle and usual cycle. So now, is it clear? Is the definition of Hamiltonian cycle clear to everyone? Okay.
Yes, ma'am. But application this Hamiltonian cycle,
Sorry.
application or any example of Hamiltonian cycle.
Okay. So I right now I don't have an application, but in next lecture I'll let you know the application of both the Eulerian trail and Hamiltonian cycle. Okay.
Ma'am, can I give one example for the Hamiltonian cycle
Yes,
basically
sure.
where we are?
Yes, sure. Yeah.
Suppose basically one salesman problem is there. So salesman want to visit all the cities, basically A, B, C, D, E, F. These are the cities.
Okay. Yes, yes.
So in that case, basically he is trying to find out that Hamiltonian cycle for which starting at vertex A and after visiting all the cities, basically B, C, D, E, F, then after visiting all the cities, he came at the starting cities. So ultimately, he is finding the Hamiltonian
Cycle
cycle in
graph.
the
Okay.
graph structure, basically.
Okay, yes, yes, very, yes, so very good. So basically he's so similar, so say he is telling the salesman problem. So any problem, in any problem like this, so if you have basically some cities and there are some connections in the cities, and those connections will denote the edges. Now if you want to see if you can find a path in which you cover all these cities at exactly once, and you start from a city and come back to the same city, then that is equivalent to saying that you want to find a Hamiltonian cycle. And similarly, any general problem which can be any general problem any general problem which can be made into like this, where you can look at assign something to the vertices and assign something to the connection, and you want to visit all the vertices exactly once, and with starting from one point and ending at one point, then that will be an Hamiltonian cycle, the
Yeah,
equivalent.
yeah, but I have a small issue here that in the traveling salesman problem, this is an optimization problem. So wherein the cost has to be minimized.
Yes, okay.
So even though we are visiting every city exactly once, but then simultaneously we are minimizing the cost of the
Yes,
traversal as well,
yes,
and
yes,
which is not the case here.
yes.
So yeah, so at the most Hamiltonian can be viewed as
But
a
there can be a sale, like, see, that is one salesman's problem when you're optimizing the cost. But there can be but there can be a different salesman who doesn't want who just want to know if there is if there is a path or not, like if there is some way where he can traverse all the city and one, and if there is no cost related to it.
Yes,
So
like say visiting a zoo, so wherein we would like to see every animal exactly once, right?
yes.
Yeah, so that.
Yes, so I'm saying that any general problem in which you can find, if you can assign some vertices and some edges, and if you want, and in that problem you want to go to each vertex exactly once, start from some vertex and come back to that vertex again, that is a problem. That problem relates to finding a Hamiltonian cycle in that graph. Okay, so now, and okay, so now, yeah, so now the now we have a sufficient condition for a Hamiltonian graph. So if a degree of each vertex is greater than equal to n by 2, then we say that G G has a Hamiltonian cycle, or G is or G is a Hamiltonian graph. But unlike the Eulerian condition, this is not a necessary condition. So for Eulerian graph, we by just looking at the degree of just looking at degree of each vertex, we could tell whether that graph is Eulerian or not. But we have no such nice condition for Hamiltonian graph. We just have a sufficient condition which says that if each if each vertex has degree greater than equal to n by 2, then that graph will have a Hamiltonian cycle. But the converse need not be true. So can anybody give me an example which shows that this is not a necessary condition?
So take the example of a cycle, and
Yes.
cycle clearly is Hamiltonian one and not following this condition.
Yes, very.
So
Yes.
by the way, what's the meaning of a sufficient condition, and what's the difference in between necessary and the sufficient condition?
Okay. So see, we have this condition. If in a if it by sufficient condition we means that uh, P is a sufficient condition for Q if P implies Q. That is, by P, then we say that P is a sufficient condition. That is, if P is true, then Q is true. So P will be a sufficient condition for Q. So in this case, we see that in this we see that having an Hamiltonian cycle, for having an Hamiltonian cycle, each vertex having degree greater than equal to n by 2 is a sufficient condition.
So does this mean that if the condition is true, then definitely there would be a Hamiltonian circuitry, and
Yes.
if the condition is false, then anything can happen?
Yes.
Yeah.
Yes. Yes.
All right.
That is to say.
Fine.
So which is more stronger, ma'am? A necessary condition is more stronger.
Yes. So you see, necessary condition is stronger in the sense that if the necessary condition does not hold, then you can say that, so basically Q is a necessary condition for P, and we also have that not Q will implies not P. So necessary condition is stronger in this sense. If necessary condition does not hold, then we can say that P will also not hold.
Sufficient means it may or it may not. Now,
Yes.
sufficient means
Yes. Okay. So now is everyone clear about this? What is an Hamiltonian cycle and the statement of the theorem? Is there any confusion in this?
so, ma'am, to prove that Hamiltonian, we have to then need something else other than this condition.
Yes. So see, so basically, if each vertex has degree greater than equal to n by 2, then you can easily claim that graph will have a that graph will be Hamiltonian. But yes, to say that it is not Hamiltonian, then you'll have to look for something else. So there is one condition which might which is one of your practice problem also, that is, if G is Hamiltonian, so we have one necessary condition also, that if G is Hamiltonian, S is a subset of vertices, S is a subset of vertices of G, then number of connected components, the number of connected components of G minus S should be less than equal to order S. So this is a necessary condition, that if G is Hamiltonian and if we take any subset of vertices, so then the number of connected components should be less than equal to the number of vertices that we are removing. So if we are removing one vertex, okay, wait. Yes, so if we are removing one vertex, then the number of connected components should be less than equal to 1. That means the graph should be connected. And if we are removing k vertices, then the number of connected components should be less than equal to k, if G is M. So this is a necessary condition. So does everyone understand the necessary condition also?
Ma'am, one example, please, ma'am.
Yes, we'll be doing some, in the questions we'll be doing these examples. Okay. So I'll, okay, I'll just,
Ma'am, why it is true?
okay, so
Can
why it is true? Yes, we can. So see, if G is Hamiltonian, if G is Hamiltonian, then G has a Hamiltonian cycle, right? Hamiltonian cycle. That means if you have n vertices, then you have a cycle of which is covering all these vertices, right? This is a basically, this cycle is contained in G. Now we'll prove this by induction. Okay, we can see by, so if order S equal to 1, if I am just removing one vertex, can this graph become disconnected?
Yes.
no,
How? How?
no,
No,
How?
no.
No, right? Because if I remove one vertex, so this is a cycle. If I am removing one point, then all other vertices are still connected, right? So for S equal to 1, we see it is true. So for S equal to 2, now if I remove two vertices, sorry. So if I remove two vertices, so this is a some cycle. Okay. So if I am removing two vertices, so there can be two cases. Suppose I am removing these two adjacent vertices, then how many connected components are there?
One.
One. And if I am not removing these two, if I am removing this, if I am removing the
Two connected
red
components.
vertices, then two. So we see if we are removing two vertices, then then the number of connected components is less than equal to 2. And similarly, you can generalize. So if you are removing three vertices, you are making at most 3 cuts. So now is this clear? Why it is true?
Yes, ma'am. These two base cases are clear, but we have to generalize by induction.
Yes, yeah. So this, yeah, we have to. Okay. So
And
can I move on to the examples of Hamilton, like problems on Hamiltonian graph, because we have just 5 minutes left.
yeah, so what's the meaning of the necessary condition here? That if the given circuitry is Hamiltonian,
Hmm.
then this condition will hold true.
Hmm.
And if the graph is not Hamiltonian, then also quite possible that this condition may come out to be true.
Yes, yes, that is true. But this is stronger in the sense that if you are given a graph, if you are given a graph, and if you can see that by removing k vertices, you are getting more than k components, then you can directly say that that graph can't be Hamiltonian.
Okay.
Okay? So
This
like
is to prove that
this condition
graph
is,
is not Hamiltonian,
yes,
right?
yes, this condition is mainly used to show that that graph is not Hamiltonian. We'll see an example. Okay? So see, yeah. Now I am saying that this graph is non-Hamiltonian. Okay. So now basically this graph is non-Hamiltonian. Okay. So you have
Yes,
to,
ma'am, it is not Hamiltonian because if we start from the vertex A and we want to traverse all the vertices, then one vertex at least will be left out. Either E will be left out, or F will be left out, or D will be left out.
okay. Yes, why?
I just observed that if we start moving from A, then first we go to F, we go to C, we go to B, we can go to G. From G we have to go back to A to go to either E or D. We
Hmm.
cannot traverse all the vertices in one go in this graph.
Okay. So that is an observation. Okay. But that is still not a proof. So let's try. So if we want to prove that this is non-Hamiltonian, we one way is to use that necessary condition. That is, remove k vertices, remove k vertices, and if you get k plus 1 components, more than k plus 1 components, then G is not Hamiltonian. So now look at this graph and try, first see if you are first see if we can use this condition to show that this is non-Hamiltonian.
We should remove the C vertex so that we will have two connected components and it will prove that it is not Hamiltonian.
Okay, so if you are removing C, if you are removing C, then the resultant graph is this, right? This is your resultant graph. And there are more edges also. So see, if you are removing C, it is still connected. So you can so by removing C, you are not getting this condition. So if you are removing C, the remaining graph is still connected. So you can't remove like, so you can't do it for C, right? So try doing something else. And it is not necessary that you have to just remove one vertex. If you after removing two vertices you are getting three components, then also you can show that this is non-Hamiltonian. If removing three vertices is giving you four components, then also it is done.
So should not we remove a vertex which has got the highest degree here? At least we would be having higher chances of getting more number of the components. Like say if we remove G from here, then probably.
Yes, yes, but it will have more chances, but yeah, even if we that is true, we can try by removing the higher degree vertices, then there will be more chances. But let's see, if we remove G, if we remove G, then also this graph is connected. So maybe maybe removing one vertex is not helping. See, if you are removing G, then also this graph is connected because you have this big square and E and F is connected by A.
Remove one more. Say the G is having the highest degree, and then after G we are having the vertex C is having the next higher degree. So if we remove G and C both, then
If we
uh,
are removing G and C both, then how many components are we getting?
so if we remove, actually it
Then
is very difficult to see from this figure. The figure is so complicated.
yes, okay, let's see.
If we,
I'll
if we remove C, G, and A, we will get four components.
yes, okay. So if you are removing G and C, see, then also it is not solving the problem because
G, G, C, A.
this is not solved. Oh, yeah. But if you remove G, C, A, yes, right. If we remove G, C, A, then we are getting four components because all the edges, all the E is, yeah. So if we take S to be G, C, A, then we are getting G minus S has four components. Therefore, we can say that G is not Hamiltonian.
Nodes now E, D, F, and B. There only nodes will be left.
Okay, so but if you are removing E, D, F, B,
No, if we remove G, C, A, then only four points are remained.
yes, that's why, yeah, only 4 points are remain. So therefore, it has four components, right?
Yes, yes.
Yes. So that we get it. So we see that this is non-Hamiltonian. We remove three vertices, but we are getting four components. So is it clear to everyone why it is not Hamiltonian?
Yes.
Okay. Uh, so that was all for. These were the all questions. Okay. Sorry. Any doubts in any of the questions that were solved today?
No, ma'am, one more thing. Can you please give the PDF of whatever
Yes,
you have
yes,
taught?
yes. So on NPT, after some time on the where you see the, and when you open your NPTEL, there will be a column on problem solving session also. It will be and there will be a link for YouTube video in that same, and also the PDF. So this session is also recorded. So we'll be uploading them on YouTube, so you can watch it again, and this PDF will also be uploaded.
Madam, yesterday session and today's session is same, ma'am. I missed yesterday
No,
session.
no, they are different sessions and different problems are solved. So someone other you should if you can, you should attend both the sessions because both are different sessions.
Okay, thank you, ma'am.
Okay,
Thank you so much, ma'am. It was
okay,
a very useful session. Thank you.
okay, okay,
Thank you.
okay. Thank you, everyone.
Thank you.
Thank you.